how to obtain the moment generating function for the Poisson distribution. Of course, this is a discrete case. It's quite simple. This is the distribution, and this is the moment generating function. So what we do is just to take the distribution and put into the moment generating function. How do we go about that? We say m xt is equal to the summation of x ranging from 0 to infinity exponential tx dot. So we bring down the distribution to put here lambda x e raised to the power of lambda all over x. So as we can see, there is something common between this function and this. So we put this back to get exponential minus lambda summation of x ranging from 0 to infinity. We combine this and this to give us lambda pt raised to the power of x all over x. Nothing has changed. But from Taylor series, we'll notice that we can bring this exponential function to give us something like this. 1 plus lambda et 1 all over 1 plus we go again lambda et 2 and it continues in this way. If it continues like this, it means that our m xt will be equal to e lambda. If we are multiplying, we'll get something like this. E, which is the exponential function, to give us its. Of course, from indices, we can rearrange this to give us our m xt to be exponential. We bring this first minus this function. We can add them. Since there is a negative sign here, we say minus lambda. So this is the moment generating function for the Poisson distribution. Also, we can look for the expected value, which is the mean, and the variance for the Poisson distribution. For we to do that, we should note that the first moment, which is equal to the expected value of x at t equal to 0, will give us the mean, which is the expected value. While the second moment, or the second differential, which is equal to the expected value of x squared at t is equal to 0, will enable us to look for the variance of x, which is equal to the expected value of x squared minus the expected value of x all squared. So if we look for the expected value of x squared and look for the expected value of x, we now impute it into this variance of x. We can now get our variance. How do we go about that? For we to get the first moment, we have to differentiate this function. So it means the first moment, which is also the expected value of x, implies that we say for we to differentiate this, we say let u be equal to lambda et minus lambda. So u is the whole of this, and y is equal to exponential u. So when we have this, we now say the u all over the t, we differentiate it with respect to t. If we differentiate this function, we get lambda exponential t minus 0. Also, if we differentiate this, the y all over the u, we get this same function, e raised to the power of u. So what we do is that we continue here. Continue there. So from here, we got that the y all over the t is equal to the y all over the u multiplied by the u all over the t, which gives the y all over the u is exponential raised to the power of u multiplied by the u all over the t, multiplied by lambda exponential t. Of course, we know that our u is equal to this function. So if our u is equal to this, we just bring it down, and the y all over the t will be equal to exponential raised to the power of lambda et minus lambda multiplied by lambda et. So this function here is the first differential. That means the first moment, which is also the expected value of x, is equal to this function, exponential lambda et minus lambda multiplied by lambda et. We also said for we to make this exponential, this function here, that means the mean, for it to stand alone as a mean, we need to make t to be equal to 0 in the function. It means at t equal to 0, which is the expected value, it means anywhere we see t, we put 0. So it will be e lambda exponential raised to the power of 0 minus lambda multiplied by lambda e 0. Of course, e raised to the power of 0 is equal to 1. Just like a raised to the power of 0 is equal to 1. So our expected value of x will be equal to e lambda minus lambda multiplied by lambda, because this is 1. So which implies that e raised to the power of 0 but lambda. That means the expected value of x for the Posson distribution is lambda, because this is 1. 1 multiplied by lambda is lambda. Also, for we to get the second moment, that means the second differential, we have to differentiate this function using the product rule in differentiation. So let's write out the first moment differential, which gave us e lambda et minus lambda multiplied by lambda et. So from product rule, we take this as a function and this as another function. We use v du all over the t, we are differentiating with respect to t, plus u dv all over the t. So we use this function. Let this be our v and this be our u. So the second moment, which is the second differential, is also equal to the expected value of x squared, which is, we say, v, we bring down v, multiplied by the u all over the t, which is this. If you differentiate this function, you get the same thing because of the exponential function, plus u then the v all over the t, which is this. If you differentiate this, you get 1 over et but you differentiate this value here, it gives lambda t minus 0. So that is it. So at t equal to 0, we have at t equal to 0, it means anywhere we see t, we put 0. We have the expected value of x squared will be equal to lambda. Anywhere we see t, we put 0. That's 0 plus lambda e 0 plus 0 minus lambda plus lambda is 0. So of course, e raised to the power of 0 is equal to 1. So it means the expected value of x squared will be equal to exponential lambda. This is 1. We have lambda minus lambda because these are gone. 1 multiplied by lambda is lambda. But this is gone too. Plus this is gone. But lambda, this is 1. 1 multiplied by this is the same thing, minus lambda. But this is 1. 1 multiplied by this is this. So we have this to be 0 multiplied by lambda plus lambda multiplied by 0, lambda minus lambda, that's lambda, which is equal to, this is 1. 1 multiplied by this is this, plus 1 multiplied by this and this is this 2. So we have this and this to give you lambda squared. It means the expected value of x squared is equal to lambda plus lambda squared. How we can get the variance? We know that the variance of x is equal to the expected value of x squared minus the expected value of x all squared. So it's very simple. We have our expected value to be lambda and our expected value of x squared to be lambda plus lambda squared. So we just substitute all of this into this to get this. The value for x ex squared is lambda plus lambda squared minus the expected value of x is just lambda all squared because of this. So if we open the brackets, we have something like this. So lambda squared minus lambda squared, this can cancel this to give us our variance of x to be lambda. So the expected value, which is the mean for the Poisson distribution, is lambda for the discrete case. And the variance of x for the Poisson distribution for the discrete case is also lambda.